Professor, for your kind introduction. And at the outset, I would like to thank the Indian Academy of Science for the opportunity to give a talk here on the topic on coordination chemistry of diboranes 4 and 6. So I feel very bad that what I'm going to talk is not anything related to applications or patent innovation. This is completely fundamental work. And what an inspirational talk just Professor Rao given now. So I will just in 15 minutes going to talk about some of the recent work on typically one of the very textbook materials you all know it, diboranes. And I'm going to show you some coordination chemistry of the diboranes that we have synthesized. As you know that boron being next to a carbon in the periodic table, it has a lot of similarities in terms of their the molecules. Particularly, I have shown some of them. All of them you have find it in the carbon family. But another thing that the boron has, which carbon cannot offer, is the various a bonding because of the electron deficient nature. It can offer a different types of bonding, and that can make a boron a very unique element when it comes to the bonding as well as a different structures. We have an account recently, we have covered many of those things there. Now, what we typically do to make this coordination chemistry with the diboranes, we make all these different transition metal, a cyclopentadienyl chloride molecules. They are extremely air and moisture sensitive. So being in Chennai with a very humid area, to make this molecule is a big challenge. Nonetheless, we made many of them. Some of them we also purchased from a company. So what typically we do, we take this molecule and simply treat them with a lithium borohydride. And it's a very fast metathesis reactions that lead to the formation of a metal polyborohydride. Now, this can go in a two different way. One can release hydrogen, another one can release the boron, and that lead to the metal hydride. And another starting material people had used it in a long back, that was the pentaboron, which turned out to be rocket fuel in 50s and 70s and between US and United States. USSR and United States, the rocket race. Okay, nonetheless, we had utilized this metal poly chloride compounds, and what you see here in this slide is the early transition metal and the late transition metal difference in terms of product distribution. As the late transition metal that has a more number of electrons, you do not need many electrons to fulfill in the to form these compounds, and you end up getting all these closed type of clusters. Whereas in the early transition metal, where you have a less number of d electron and you need these hydrogens, that makes this molecule extremely air and moisture sensitive. So I'm going to talk a little bit on this molecular boron type of chemistry with one or two boron. Another area that we also had explored is a different type of sigma borate and bis sigma borate complexes. As you see here, this is a bis sigma borate complex. Then you have a borate complex that is activated by a silane molecule. You have a phosphorus activation, you have a hydroboration reactions. I'm not going to talk about this. This is some of the research interest that we have been working in IIT Madras. So as I was talking about the diboranes, you all have seen this one in the textbook, the diborane 6, in which a banana shape of bonding. So the diborane 4, you have 4 hydrogens and with all these different symmetries. It's starting with the D2H, CS, D2D and C2B, except this CS symmetry, which was not structurally known. So that one also, after our synthesis, it fulfilled all these molecules. The first molecule, it was 2014. It was a mimic of this molecule that was made by Sheldon Shore in Ohio State in 1989. In this case, one of the hydrogens that could simply replace a CP2, as a CpFeCO2, And in this case, you have your ruthenium Cp star and this 2 sulfur. In terms of the electron, 18 electron is count, is completely fulfilled as that of this molecule. So then we move to a different transition metal with a molybdenum, and one of the molecules we selected, it was a diborane 6. We treated with the CO gas, and it leads to the formation of a diborane 4. However, as you see the bonding of this diborane 4 with the molybdenum Cp star, it is a different kind of bonding, and that's why this molecule is extremely fluxional, in which you have a molybdenum Hb and this side molybdenum Hb that fluctuate between these two transition metals. We are fortunate to have the structure of this one. This is exactly what I was talking about. This is the CS symmetry of the B2H4. Now with this, all these 4 different B2H4 now have these extra structures known. Now this is the same molecule that was made by F.A. Cotton in 1978 with molybdenum with the acetylene. Now we can call this as exactly mimicking of our B2H4 that we had made with molybdenum Cp analog. Now this B2H4, which is the CS symmetry, and this gives 4 electrons to this the coordination pair of these 2 molybdenum, and indeed we had done the calculation with GEMIS for the theoretical support. I am not going in details for this study. Now the next one, I wanted to show you how this B2H4, this is the one I was talking about, can be utilized treating with the tungsten CO5 THF that can take up 2 of the hydrogen and make B2H2. So this molecule, if you look at the bond distance of this BB, in this case this is 1.6 and this is 1.71. So that clearly tells about the BB bond distance nature, though this is a typical of BB double bond and this is a BB single bond. So we convert a diborane 4 to diborane 2 where you have a BB single bond to BB double bond. Now this is one of the very important problems we have been thinking about, a classical diborane. What are the diboranes known in the literature is all non-classical, in which you have a BHB bond. All these molecules, particularly the coordination chemistry of this diborane, are known all in the non-classical categories. So we wanted to synthesize something different with a tantalum, and while working on this, what we observed that this molecule, I am not going in details, but if you look into the extra structure of this diborane, this one is actually a classical B2H5 minus. So this is the first time we have synthesized a classical B2H5 minus in which you have no BHB bonds. So again, this was done in collaboration with GEMIS. It was a very challenging problem to solve, whether it was a B2, a classical or non-classical mode. So he did a very thorough calculations, and that clearly shows that this is the classical one in which you have a tantalum H tantalum hydride bond. We also wanted to utilize the same platform to remove 2 hydrogens, and what we observed that instead of taking 2 hydrogen, it simply coordinate with one of the boron. And what we observe here in this case is that earlier we have removed hydrogen, now in this case molybdenum coordinate with this boron. Now once it coordinates with this boron, now you see the boron chemical shift immediately move to the downfield region, and this molecule also switch between these 2 tantalum, and you could see that. So this is the calculations, and we have also experimental support that clearly shows at a lower temperature you can get a 2 different Cp star and all the different characteristics hydrides that been resolved out. So interestingly, this year, when 2019, we reported this molecule, Douglas Stephen, who is known for the frustrated Lewis pair concept, he also made this molecule with a diborane B2H5 cation. So in the same year, 19, as you could see that we had a diborane B2H5 minus and also a B2H5 cation. Now, The diborane molecule also, there are many where you do not need a metal to coordinate with them. There are several of these, and many of groups are working in this area. I have listed Matthias Wagner, Himmel, Fontaine, Douglas Stephen, Holger Braunschweig, many more. And again, the same thing with the same four different symmetries of this diborane 4. So what we have been working on this to make from a mercaptopyridine and treat it with a borane at higher temperature. In most of the cases, your diborane of this type, you need to utilize a catalyst to make this, but in this case, we have not used any catalyst, but you could see that we have two different types of diborane. Now, this one you can call is a doubly best stabilized diborane 4, where you have this nitrogen and this nitrogen, it gives it electron, the dative bond. But this one is a completely different and unique. And this one you cannot call is a diborane, rather you can call this is a boronium cation. So this is a borate, and this one you can call boronium. So you have a boron 1 and the boron 3 species, but in this case you have a simple diborane system. We have done calculation, and as you could see there, the natural charges in this case are different, and in this case you have the same. And once we had this diborane best stabilized, we treated with the chalcogen powder, and you can see that a chalcogen element starting with the sulfur selenium, you have an oxidative addition to form a chalcogenado adduct with this diborane 4. So this is the summary of this study, in which you have taken a simple mercaptopyridine or benzothiazole, you treat with the borane, and you get two different types of diborane. One is a borate boronium, another one is a base stabilized diborane 4. Just last 2 minutes, this is something, like I have been, since I started my career in IIT Madras, we wanted to make a planar B6 molecule, and there's a lot of difficulties. Most of them have been isolated in a matrix, and the theory, including a GEMIS, many of them, what they had suggested that you can only isolate this flat B6 if you have a fragment of a vanadium and titanium in a reverse sandwich, inverse sandwich mode. So we did this, and it's a long story short. A titanium Cp star Cl3, you take with lithium borohydride followed by cooking with borane, you get a B6, and rest of the spectroscopic data, everything, it is crystal clear. As you see, this is only one boron peak. We have a HSQC that clearly tells about a one type of titanium HB is an alternative boron. And this is not a fluxional molecule, very straightforward, and this is a B6 molecule. So now this is the first time we had shown that a B6 can also, most of the cases, as you have seen in the textbook, that B6 H6 2- it's an octahedral geometry, but we have made first time with the help of a titanium Cp star to make this B6 as a flat. In the same year, Stephanie Denon made this molecule with the bismuth, and Cameron Jones made the aluminum 6. In both the cases, what you see here, this is a octahedral, and this is a trigonal prism with a 6 bismuth atom. So what interesting in this case in the Stephanie's molecule is that this molecule shows a 5 type of aromaticity in the prismatic B626, B6 bismuth 6-2-. I do not understand much of this aromaticity, so I will not go in details, just to wanted to connect you with how this different element with the geometries shows different property. This is my last slide. Along with the formation of this titanium B6, we have also isolated another molecule. This is a first time we have shown that this could be considered as a molecule in which the parent molecule is a 19 vertex. So this is the first molecule in which we have a single cage in which have a hypoelectronic nature. So we recently, in collaborative with the T. Pradeep and Thomas Bass in Czech Republic, we had this a B18 scene isomer. And one of the co-authors in this paper, Jonathan Bole, whom I know for long years, for 20 years. So he asked me to send this molecule and see if we can trap with this scene or anti-B18 and get a different kind of properties. As you could see that it's a beautiful luminescence properties. So with this, I would like to thank my entire group that really work on the particular very difficult areas. Many of them in academics now, and these are the current group. And my collaborator, particularly, I would like to thank Jemis, who has been in support of last 25 years. Lai Seng Wang in Brown University for those molecules with the property of the B6, and Arnav Datta IIT Bombay for some of the studies, and my big thank to Babu Varghese, who helped me solving many of the problematic structures that we had isolated, and all these funding agencies for a continuous support to do a very fundamental chemistry. And thank you very much for your time.